the Tiger. Even for those with only a passing interest in military history, the name itself carries an immense weight. It's a 57-ton symbol of technological terror that dominated the battlefields of World War II and defined raw, armored power for a generation. It's the tank that fuels endless debates, the star of countless documentaries, and the unassailable benchmark against which all other World War II tanks are measured. This is the Tiger 131, the last running Tiger 1 in the world, meticulously maintained at the Bovington Tank Museum. When you look at it, you can feel its reputation. It's a monument of thick, flat, intimidating steel. It looks almost invincible. And this is the Leopard 2A8, one of the newest, most advanced, and most complex main battle tanks on the planet. Alongside its contemporaries, the American M1A2 Abrams, SCPV-3, and the British Challenger 3, it represents the absolute apex of 80 years of brutal, expensive, and relentless evolutionary development. We look at the Tiger, and we look at the Leopard, and we ask a simple, fundamental question. How much have tanks really improved? Is the new one 10 times better? 100 times better? Well, to understand how we got from that to this, we must first deconstruct the legend. We have to move past the mythos and understand what the Tiger really was. The Tiger 1's reputation was built on two simple, terrifying facts: its gun and its armor. The gun was the legendary 8.8cm KWK-36. This was an adaptation of a high-velocity anti-aircraft gun, and it was phenomenally accurate and powerful for its day. It fired a heavy projectile at a high velocity, allowing it to kill most Allied tanks at ranges where they were completely unable to fight back. The armor was 100 to 120 millimeters thick at the front, virtually immune to the 75mm guns found in the vast majority of Allied Sherman and T-34 tanks at the standard combat ranges. An Allied tank crew would have to get perilously close in a flanking maneuver to have any hope of penetration. But that's the legend. The reality of operating a Tiger was an analog, mechanical, and logistical nightmare. Let us, for a moment, analyze the process of combat from the perspective of the Tiger's 5-man crew. We can start with the gunner in 1943. He's looking through a binocular optical sight, the Termzi Fernrohr 9B. He is, in effect, looking through a telescope with crosshairs. He sees an enemy tank in the distance. How far away is it? He has absolutely no idea. He has to calculate it. This was a process called stadiometric range finding. In his sight are small lines, or mills. The gunner has to know the exact size of his target. He has to know, for example, that a T-34 is 2.72 meters tall. He then has to see how many mils that T-34 fills in his sight, and then perform a mental calculation, often using a predetermined chart, to get an estimated range. Okay, he is 2.72 meters tall, he fills 2.5 mils in my sight, so he's probably 1,090 meters away. This was a skill that took time and was prone to error, and it was all done under the immense stress of combat. Once he had his guess, he would crank his manual elevation wheel to set the gun for 1,090 meters. He would then traverse the heavy turret using a hydraulic drive, which was powerful but imprecise. He would have to use fine-tuning manual hand cranks to get the crosshairs perfectly aligned. Now, let's consider the driver. The gunner must tell the driver to stop the tank. The Tiger had zero stabilization. If the gunner tried to fire while the tank was moving over a field, the gun would be pointing at the sky one second and the dirt the next. The stop and shoot doctrine was a physical necessity. While all this is happening, how does the commander find targets? He's half blind, peering through narrow, thick glass vision slits in his cupola. These slits were tiny to prevent bullets from getting through, and as a result, his field of vision was abysmal. To really see the battlefield, he had to do one other thing no soldier wants to do: open the hatch and stick his head out, exposing himself to shrapnel and snipers. And all of this was in broad daylight, in clear weather. At night, the Tiger was blind. In fog, it was blind. In a smokescreen, it was blind, and it had no way to see beyond the visible spectrum. The mechanical reality was, in many ways, even worse. This 57-ton beast was a logistical catastrophe. It was rushed into production, massively overweight, and its complex components weren't designated to handle the strain. Its engine, the Maybach HL230, was a powerful V12, but it was being pushed to its absolute limit to move 57 tons of steel. The tank's transmission, a complex, pre-selective hydraulic unit, was prone to catastrophic failure. Its famous interleaved road wheels, which gave it a smooth ride, were a maintenance nightmare. In the mud and ice of the Eastern Front, mud and snow would pack between the wheels and freeze solid, immobilizing the tank. A simple repair, like replacing an inner road wheel, could take a maintenance team hours or even days. For every Tiger terrorizing the front, another was likely abandoned by its crew, broken down behind the lines with a failed transmission or a blown engine. But the single biggest, most terrifying flaw of the Tiger I and of virtually all World War II era tanks was what happened when the armor failed. The ammunition, the big brass-cased 88mm shells, are everywhere. They're in the hull, in the turret, in sponsons right next to the driver, and at the gunner's feet. The crew is literally surrounded by tons of high explosives and propellant. When an Allied shell managed to penetrate that thick armor, it wasn't always the explosion that was the deadliest part. It was the spall. The impact would cause the inside of the Tiger's own armor to splinter, sending a cone of red-hot, razor-sharp metal fragments ricocheting around the crew compartment. If one of those red-hot fragments hit a stored shell, it would ignite the propellant. This would, in a fraction of a second, trigger a chain reaction, igniting all the other shells. The result was a catastrophic, instantaneous explosion called a brew-up or a jack-in-the-box. The overpressure inside the turret was so immense that it would blow the entire multi-ton turret clean off the hull, killing the entire crew in a millisecond. This was the reality of the analog thick steel era. The entire design philosophy was to make the armor so thick that the tank was invincible. There was no plan B. So, our baseline is a tank that is mechanically unreliable, blind at night, has to stop to shoot, relies on manual guesswork to aim, and is a rolling coffin if its armor is ever breached. Now, compare that with the main battle tanks of today, like the Leopard 2A8, the M1A2 Abrams, SEPV3, and the Challenger 3. On the surface, they share the same DNA, a tracked, heavily armored vehicle with a big gun. But that's where the similarity ends. Let's start with the basics, the chassis. They're heavier than the Tiger, often 65 to 70 tons, but they're infinitely more mobile and reliable. The M1 Abrams uses a Honeywell AGT 1500 gas turbine, which is essentially a jet engine. It's incredibly powerful, very quiet, and can burn almost any fuel. The Leopard 2 uses an MTU MT873 diesel engine, a massive, torque-heavy, and more fuel-efficient power plant. Both are light years beyond the Tiger's strained Maybach. Their armor is a combination of thick steel and the so-called composite armor, often called Chobham armor. This is a secret sandwich of sorts, with layered steel, ceramics, plastics, and exotic materials. The hard, brittle ceramic layers are designed to shatter an incoming kinetic penetrator to blunt its force and spread the impact over a wider area. It provides a level of protection against modern threats that's vastly superior to steel. Their gun is the 120mm smoothbore cannon, like the Rheinmetall L55A1 found on the Leopard 2, and the new Challenger 3. Unlike the Tiger's rifled barrel, which spins a shell for stability, just like a bullet, a smoothbore barrel allows the modern tanks of today to fire modern anti-tank sabot rounds or incendiary heat rounds designed to deal maximum damage. These modern darts that these tanks fire are fin-stabilized darts that don't want to spin. Spinning it would just make it less accurate. A smoothbore barrel acts as a high-pressure launcher, allowing the fins on the projectile to provide the stability and enabling velocities the Tiger's designers couldn't have comprehended. But all of this is just the platform. The real revolution is the software. The Tiger was a tank. The Leopard 2, on the other hand, is an integrated weapons system. The value of a modern tank isn't in its steel, but in its systems. And those systems have revolutionized 3 things: seeing, fighting, and surviving. Let's begin with seeing. This is, without question, the single greatest leap from World War II to today. Let's go back to our Tiger gunner, sitting in the dark and blind. Now, let's sit in the Leopard 2A8's gunner's seat. The first and most important tool you have is a thermal imager. The sensor doesn't see light, it sees heat. This one piece of technology fundamentally changed armored warfare. It gives the modern tank crew a decisive, almost unfair advantage. It means they own the night. A modern tank can see an enemy tank hiding in a bush because its engine's heat signature bleeds through the leaves. It can see through smoke, it can see through fog, and it can see through darkness. The Tiger was blind in all 3. A modern tank crew can fight 24/7 in any weather with perfect clarity. So now, the gunner sees his target, a white-hot silhouette of far away. How does he hit it? He puts the crosshair on the target, which activates the laser rangefinder. An invisible to the naked eye beam of light shoots from the tank, hits the target, and bounces back. The tank's computer measures the nanoseconds it took for that light to return, and because the speed of light is a constant, it instantly calculates the exact range. It's 3,012 meters. The LRF removes all guesswork and provides perfect, instantaneous data. This range data is fed instantly to the ballistic computer, the digital brain that does all the complex math that our Tiger gunner had to do in his head. But it's not just the range. This computer is pulling data from a whole suite of sensors all at once. It gets the 3,012 meter range from the LRF. It gets the wind speed and direction from a crosswind sensor on the turret roof. It gets the air temperature and barometric pressure from an atmospheric sensor. It gets the temperature of the ammunition propellant from a sensor in the ammo storage. It even gets data from a muzzle reference system, which is a tiny laser at the end of the gun barrel that measures its droop. A long, heavy gun barrel bends slightly from heat and gravity, and the computer knows this and compensates for it down to the millimeter. The computer takes all of this data, does the complex calculations in a microsecond, and instantly lays the gun, adding the perfect amount of elevation and lead. The gunner doesn't have to think about it. He just keeps the crosshair on the target. And then, of course, there's stabilization. The gun and the gunner's thermal sight are mounted on a complex gyroscopic system, which means the tank can be bucking and rocking, climbing a hill or speeding across a field, but the gunner's sight and the gun itself remain perfectly level, locked on to the target. This means that a modern tank crew can be speeding across a battlefield at 70 kilometers per hour at night in a smokescreen, spot a target 3,000 meters away with their thermal imager, get the exact range from their laser, and let the computer aim the gun, and they can hit that target with the first shot. A Tiger crew had to stop in broad daylight in clear weather and hope their 1,000 meter guess was right. Now, let's talk about fighting. You can see the target. Now, you have to kill it. The Tiger's 88mm was a fantastic gun. It fired a big, heavy, solid bullet, an armor-piercing capped round. It used kinetic energy to punch a hole, a big hammer for a big problem. Modern 120mm smoothbore guns, like the Rheinmetall L55A1, are a different kind of animal. The primary tank-killing round is APF-SDS. It stands for Armor-Piercing, Fin-Stabilized, Discarding Sabot. Let's break that down, because every word is important. The term sabot itself comes from the French word for shoe. The projectile is a long, thin, incredibly dense dart, usually made of tungsten or depleted uranium, only about 2 or 3 centimeters wide. This dart is held in place inside the gun barrel by a lightweight shoe, or sabot. When the gun fires, the sabot's crucial job is to transfer the massive energy from the propellant to this tiny, dense dart, accelerating it to insane speeds, over 1700 meters per second, which is more than a mile per second. The discarding part of the name describes what happens the instant the round leaves the barrel. The sabot, its job done, peels away and falls to the ground, allowing the now fin-stabilized dart to continue on alone. Finally, armor-piercing, which is almost an understatement. This dart has no explosives and needs none. It possesses so much kinetic energy that when it hits a piece of steel, it simply overwhelms it. The impact superheats the armor, allowing the dart to punch its way through while spraying a devastating cone of molten metal and shrapnel inside the enemy tank. It's a kinetic energy penetrator, just like the Tiger shell, but taken to its absolute, horrifying extreme. But what if your target isn't a tank? What if it's infantry in a trench or a machine gun in a building? The Tiger had 2 main rounds: armor-piercing targets, which were for heavily armored targets, or high explosive for soft targets. You had to pick. A modern tank, thanks to its digital fire control system, even has programmable ammunition. The fire control system can talk to the shell as it's being loaded, programming its fuse for a specific task. The first and most revolutionary mode is the airburst mode. The gunner uses his laser rangefinder to laze the infantry hiding in a trench. He then lasers a point just beyond them. The ballistic computer understands the command, and as the shell is loaded, it programs the fuse. The shell flies over the trench and then explodes in midair, raining thousands of tungsten balls or shrapnel fragments down on the exposed soldiers. The second mode is delayed fusing. The gunner wants to hit a sniper in a building. He programs the shell for delay. The round will punch a clean hole through a concrete wall and then explode inside the room, maximizing its effect. The third is a standard impact mode. The gunner wants to blow up a truck, and he programs the shell to explode on contact like a normal high explosive round. And this brings us to our final and perhaps most profound change: surviving. This is a philosophical shift. The Tiger, as we discussed, was built on the philosophy of protection. The idea was to bolt on so much thick, heavy steel that nothing could get through. But it was a passive, brittle defense. If it failed, the crew was dead. Modern tanks are built on the philosophy of survivability. The design accepts that the tank will be hit. The entire goal is to make sure that when it is, the crew survives to fight another day. This philosophy is built on several revolutionary layers of defense. The first and most important is isolated ammunition. Remember the Tiger with its crew surrounded by ammo? Well, let's now look at the Abrams or Leopard. The vast majority of the ammunition is not in the crew compartment. It's stored in a separate, heavily armored bustle on the back of the tank, sealed behind thick, blast-proof doors. The crew is compartmentalized and isolated from the explosives. This leads to the second feature: blow-off panels. If an enemy round does hit that ammunition bustle and starts a fire, the blast-proof doors stay sealed, protecting the crew. And the roof of the ammunition bustle, which is intentionally the weakest part of that compartment, acts as a blow-off panel. The entire catastrophic explosion of the brewing up ammunition is vented upwards away from the tank and the crew. A 1992 US Government Accountability Office report analyzing the M1's Abrams performance in Desert Storm, detailed multiple instances where Abrams tanks sustained hits to their ammunition compartments. The blow-off panels functioned exactly as designed, venting the explosion and allowing the crew to climb out, often shaken but alive, from a tank that would have, in any previous generation, been an instant, fiery tomb. But survivability goes even deeper. Modern tanks are lined with spore liners, materials like Kevlar, designed to catch the deadly fragments of metal, spore, that are knocked off inside the armor when it's hit. This prevents the metal bender effect that killed so many crews in World War II. Furthermore, automatic fire suppression systems are everywhere. Sensors within the crew compartment can detect the flash of a penetrating round or an internal fire in milliseconds. Before the crew can even react, the system floods the compartment with a fire extinguishing agent, putting out the fire in less than a second. But there's one final revolutionary layer of defense, a layer that truly separates the modern era from everything that came before. The Tiger's defense was passive. It had to sit there and take the hit. A modern tank's defense is active. The Leopard 2A8 and many modern Abrams are equipped with active protection systems, or APS, like the Israeli-designed Trophy. You can see the small, flat radar panels on the turret. These panels are constantly scanning 360 degrees around the tank. When an enemy soldier fires a rocket-propelled grenade or an anti-tank missile, the Trophy's radar instantly detects it. The computer calculates its trajectory and speed in milliseconds, determines if it's on a collision course, and if it is, it acts. When the missile is just a few meters away from the tank, the system shoots it down. The Trophy launcher, which is a rotating projectile launcher, swivels to face the threat. It fires a countermeasure, a special projectile that detonates and fires a shotgun-like blast of small penetrators into the incoming missile, shredding it in midair before it even hits the tank. So let's go back to our original question. How much have tanks really improved since World War II? Well, the answer is, they're no longer the same thing. A Tiger was an analog machine. A Leopard 2 is a digital one. A Tiger was a daylight-only, stop-and-shoot brawler that relied on guesswork. A Leopard 2 is a 24/7, all-weather, fire-on-the-move weapon system that relies on perfect data. A Tiger had one way to kill a tank and one way to kill a person. A Leopard 2 has a programmable, multi-tool cannon that can handle any target on the battlefield. And finally, the Tiger was built on a philosophy of protection, hoping its thick, passive steel would be enough, and if it wasn't, the crew was expendable. A Leopard 2 is built on a philosophy of survivability. It uses active defenses to shoot missiles out of the sky, and it's designed, from its very core, to sacrifice its own ammunition to save the one thing that truly matters: the crew. The Tiger is a legend. It's a magnificent, terrifying, and deeply flawed museum piece. But the modern main battle tank is a different beast entirely. Anyways guys, feel free to leave your thoughts in the comments section below, and as always, thank you so much for watching, and I hope you learned something new.